Hello everybody. Welcome to this week's sixth uh, session on control engineering. So, in today's problem-solving session, we will cover the frequency response analysis, polar and Nyquist plots, Bode plots, gain and phase margin, and this you have covered in your previous lectures and slides. I'll quickly recap what we have done till now. So we started with the time domain analysis, where we studied about rise time, peak time, settling time, maximum overshoot, etc. So they were typical time domain specifications. For example, given a system. So if you're asked whether my system is good or bad, or whether you need a system for a particular application, so you should be able to judge based on those specifications. For example, if you have a requirement of faster response, then maybe you need a system with lesser rise time. But at the same time, if you don't want any overshoot in the system, and you're okay to compromise with the slower response, then maybe there's a trade-off between the overshoot and the rise time. So based on those specifications, you are able to identify uh, like which system is good for my application and which system is not. Now, today, what we will do, so basically, we were giving some input and checking the response of my system with respect to time. Now, what we will do, we will see the response with respect to frequency. So if I have a system, if I have a system and I'll give input. So when we talk of frequency, so maybe we are giving sinusoidal input. And what we will get in the output. If it's a linear system, and we have assumed in the lecture one that throughout this course we'll be talking about linear time invariant systems. So if it's a linear system, we'll also get a sinusoidal output. Sinusoidal output. For example, if I'm giving a sine omega t at the input, I should get a dash sine omega t plus phi. So I'm getting in the output some magnitude. It may be same or different, and uh, I'm getting my response delayed by phase phi. But it's very important to see we are getting the output at the same frequency as that of input. So what we will do, we will vary frequency. So we will vary omega from 0 to infinity and observe this magnitude, that is a dash, and phase, that's phi. Correct? So in frequency response analysis, what we do, we vary frequency from 0 to infinity, and then observe how my magnitude is changing and what's happening to the phase, right? So this has its own advantages, because if you see in time domain analysis, if your order increases, it becomes very difficult uh, to study those systems in time domain. And similarly, we were not able to study relative stability in terms of in time domain analysis, or even if we do, it's very easy. It's very easy in frequency domain analysis, as we'll be seeing when we will study phase polar plots or Nyquist plots or even Bode plots. Right. So, in general, when we talked about the time domain analysis of a second order system, I wrote the CLTF, the second order system, as omega n square s square plus 2 zeta omega n s plus omega n square. Correct. So this is my closed loop transfer function. But just a minute. Okay, so am I audible?
Yes, sir. Now you are audible.
Can anybody confirm?
Yes, sir. You are audible.
Yeah, thank you. So this was my closed loop transfer function for a second order system. And now, if I want to study the same system, basically I'm focusing on second order system because the questions that you have in the assignment are these systems are very important because first order systems are very easy to study. So if we are going like if we have to do the frequency response analysis of this second order system, what we'll do, we will go from we'll go to Fourier, we'll take Fourier transform of this system, right? So for example, if it is T of S, I'll take T of J omega, which will be omega n square divided by J omega square plus 2 zeta omega n j omega plus omega n square. So I've just put my s as j omega. If I simplify it, so it will be omega n square divided by, this is minus omega square. So minus omega square plus j 2 zeta omega n s into omega plus omega n square. And if I take omega n common, so it will be omega n square omega n square 1 minus omega square by omega n square plus plus j 2 zeta omega by omega n. Correct? And this will go. I'll get 1 over 1 minus u square plus j 2 zeta u, where u is omega by omega n. Right. So I got something like this. 1 over 1 minus u square plus j 2 zeta u. So this is a complex number, right? And we know a complex number has a magnitude as well as phase. And if you calculate, so it has a magnitude. Let me denote that as like, so it has a magnitude as well as phase because it's a complex number. If I hypothetically plot this magnitude, so this is my magnitude m, and this is my omega. So if I plot this magnitude, it will be something like this. So I'm like, I'm just plotting it approximately. So this is how my magnitude varies with respect to omega. And if you see, when my omega is zero, here, I have some magnitude here, right? And it's called as DC gain because there is no frequency. So when there is no frequency and the value of magnitude at that time is called DC gain. And then we can see magnitude is increasing and reaching a peak value, right? And this peak value is achieved at this frequency, which is called omega r, right? So this uh, peak value of omega, this peak value of magnitude is called resonant peak. And this frequency at which it occurs is called resonant frequency or resonance frequency, right? So why I am recalling all this? Because at the beginning of the lecture, I told you about rise time, peak time, settling time, maximum overshoot, and based on that, you can identify whether my system is good or bad, whether this particular system I can use it in my application or not. So similarly, based on these properties, you should be able to like know how the behavior of a system is. If I'm giving you, okay, your system has a resonant frequency of this and a resonant peak of this, so so you should get an idea like how my system should be, right? So uh, uh, then we have something called as bandwidth. So if you see this area, This is an area of where the magnitude is significant, right? So the area, the region, the band of frequencies where my magnitude is significant is called bandwidth, right? So in this, so and one more thing is that we are using two types of we are plotting magnitude. Like here, we are using the values of magnitude, specific values of magnitude. But when we will study the the Bode plot, there we will see we are plotting the magnitude in decibels. So then if I have magnitude and if I want to calculate this in decibels, I will multiply it with 20 log of that value magnitude. So in order to convert this magnitude in decibels, right? So basically you have these parameters like resonant peak, resonant frequency, bandwidth, etc. And all these parameters, they have specific formula. I'm not going into the derivation of this, but I'm just recalling the formulas. So the resonant frequency, resonant omega r is given as omega n 1 minus 2 zeta square, where my zeta should be 1 by root 2 in order for resonance to occur. Similarly, the formula for resonant peak is 1 over 2 zeta under root of 1 minus zeta square. And also the formula for bandwidth is 1 minus 2 zeta square plus under root of 4 zeta square minus, sorry, this is 4 zeta 4 minus 4 zeta square plus 2 under root. So these are the formulas for uh, resonant frequency, resonant peak, and bandwidth. So if you're asked to find resonant peak or resonant frequency and bandwidth, that if you are given a second order system in generalized form or whatever be the values, you should be able to calculate, right? So now let's solve a question. Start with simple question. For example, the forward power transfer function of a unity feedback system is given as G of S is 100 over S square plus 10S plus 100. And you're asked the frequency response of the system will exhibit the resonance at. So you have to find the resonance frequency. First, you'll check whether resonance will occur or not. And if it occurs, what is the value of resonant frequency? Solution. So we know the standard CLTF, and it's given as it's a unity feedback system. So H is 1, so no need to like it's already given in that form. So we write G of S as in case of a second order system, it's like this: 2 zeta omega ns plus omega n squared. So omega n square is 100. It means my omega n is 10. Similarly, 2 zeta omega n is 10. It means 2 zeta into 10 is equal to 10, and omega is 1 over 2, it is 0.5. Correct? So you now obtained omega n and zeta. And now the formula for resonant frequency is omega n under root of 1 minus 2 zeta square, which is equal to 10 into 1 minus 2, 0.5 square. So tell me what is the value of omega n, and it should be radians.
7.07.
Great.
7.07.
7.07 is the value. So Now, coming to a question which is at the practice assignment. Let's solve this question now. The question says, considering the frequency response of a standard second order closed loop system with transfer function T of S. So we are given transfer function T of S as omega n squared divided by S squared plus 2 zeta omega n plus omega n squared. Should be S here, I think. Right, and what is being asked, and it's also given that zeta is 0.2 and settling time is 0.5 seconds, right? So you are given a second order system and where zeta is given and settling time is given. Maybe you may consider 2% band, right? So then you're asked to find the resonant peak, frequency. So resonant peak frequency means the same thing, that is omega r, which will be in radians per second. And also you have been asked to find the resonant peak, right? So peak value. And also you are asked to find the bandwidth. Please try solving this question. I'll give you one hint. We are given as TS, settling time is 0.5 seconds. And if I consider 2% settling time band, then it will be 4 over zeta omega n is equal to 0.5. It implies 4 into, what's this? The 0.5, it's given as gamma, and what's omega? Omega n. So, okay, we need to find omega n. It means omega n is 25.
So zeta 0.2.
Yeah, sorry. So omega n will be 40. So you got natural frequency. Now you should be able to calculate, like putting these values in the formulas. You already know the formulas. Please tell me what's the value of resonance frequency and peak or shoot, as well as the bandwidth. Take your time. And these type of questions are being like similar questions are asked in competitive exams. Has anybody calculated omega r? You should have calculators around. Otherwise, it will be a bit difficult.
2.55, sir. Peak.
2.55 MP. So, okay. MP is 2.55. And then what is omega r and bandwidth?
0.9591 omega r.
Um, are you sure? 0.9591. What is the formula for omega r? Omega n into under root of 1 minus 2 zeta square.
Omega n.
Do you have
Omega n we should find.
what's omega n is I have found omega n 40.
40.
Yeah. It should get it as 38.
38. 38.
That is
38.36.
cool. So bandwidth, if you solve, you will get 60.38. Right? And now let's move forward. There is one more question, but I hope that these questions are a bit easier and we should invest some this time on other problems. And if we get time, I'll come back again. Now let's see what is relative stability. We will understand gain and phase margins first, because they can be used like in Bode plot, Nyquist plot, and even Polar plots, or gain margin is even used in root locus and route criteria. So what have we studied? We first studied route criteria, where we studied system is stable if there are no sign changes in the first column of route array, right? Then we saw, okay, if we write it in terms of k, we get a range of values of k for which the system is stable, and for the other values, system is not stable, and for a value, system is marginally stable, right? So then you also saw if we have a row of zeros in the first column, then uh, there has to be imaginary roots on the there has to be imaginary roots. And if we have simple imaginary roots, then the system is marginally stable. If we have repeated imaginary roots, then the system is unstable, right? Even if there are no sign changes. And then we moved forwards and we saw root locus, where we saw, okay, if we change the value of k from 0 to infinity, how my closed loop poles, like what is the locus made by the closed loop poles then if I change my values from k equal to 0 to k equal to infinity? I said, when I was drawing a root locus plot, I said it starts from an open loop pole and terminates at open loop 0. But it gives us closed loop stability. So it gives us information about closed loop poles, right? So when you start from an open loop pole and you terminate at open loop 0, it means when it's giving us the information of closed loop poles, it means open loop poles at k equal to infinity become closed loop poles. Open loop zeros at k equal to infinity become closed loop poles. Right. So what is the crux? What is crux here is that as we increase the gain, we saw that our system, for a value of gain, it is stable. Then as we keep on increasing, it becomes marginally stable. And as we keep on still increasing, it becomes unstable, right? So that value of gain for which my system, so if I'm starting with a stable system and that value of gain for which my system goes to the verge of instability, that's called gain margin, right? For example, if I have a system whose poles are here, so it's a stable system, I'm changing the value of k. So I'm changing the value of k, it reaches here, right? Then if at some values, if I'm changing the value of k, my poles reach here. So this the amount of gain that I increased from this point, initial point, in reaching in taking my system to the verge of instability. What is verge of instability? Marginal stability. So I took my system from being stable to the verge of instability, or I'm making it unstable. So the amount of gain that is required, that's called as gain margin. So I'll define it. It is the gain margin is a factor by which the gain of a stable system is allowed to increase before the system reaches to the verge of instability. Right. So now there is this term which is called phase crossover frequency. Phase crossover frequency. Right. So the phase crossover frequency is the frequency at which the phase angle is 180 degree. It means so normally you are given a system G of S, H of S. So open loop system, open loop transfer function you are given, or in S domain, how you will write it, Gj omega, Hj omega. Then you know this is a complex number. It has a magnitude as well as phase, right? So if so it has an angle as well as phase. So the angle of Gj omega, and one more thing, I told you in the beginning, it's frequency response analysis. We are changing frequency. And then we're plotting magnitude and phase. So the value of frequency for which the angle of Gj omega H omega is equal to 180 or minus 180. This is called this is called phase crossover frequency. Please remember it because the questions will be based on this. So I'm again repeating. So the frequency at which my phase angle is 180 degree or negative 180 degree is called phase crossover frequency, and mathematically it's written like this, right? And if my magnitude Gj omega, Hj omega at omega equal to phase crossover frequency is equal to x, then gain margin is equal to 1 by x. Or I told you in the beginning, if I have to calculate in decibels, what I will do? 20 log of that value, 1 over x, it will be 20 log of 1 minus 20 log of x. So I'm again repeating. I told you, so when we increase this system gain, it goes to it moves towards unstable region. So that amount of gain, which makes my system marginally stable, is called gain margin, right? So then mathematically, how we define it, we know phase crossover frequency is the frequency at which my phase angle is 180 degree minus 180 degree, right? And the magnitude of my open loop transfer function at phase crossover frequency, if that is x, then gain margin is 1 over x, right? And in decibels, we write 20 log of 1 over x, right? Please remember this. Now, similarly, let me define phase margin. So the phase margin, I'm just writing, is that additional amount of phase lag at the gain crossover frequency. So first, let me define what is gain crossover frequency. So the gain crossover frequency is the frequency where my magnitude of Gj omega Hj omega at gain crossover frequency, it's equal to 1, right? So my magnitude of so gain crossover frequency is the frequency where the magnitude of my open loop transfer function is unity, right? And you know that log of 1 is 0, so it means if I take in decibels, it will be 0 in decibels, right? So magnitude, so it will be the value of, so my gain crossover frequency will be the value of my magnitude at, so gain crossover frequency is unity. So that value of my magnitude where my, that value of my frequency where my magnitude is 1 is called gain crossover frequency, or in decibels, if my magnitude is 0, that's called gain crossover frequency. Right. Now, if angle of Gj omega Hj omega at omega equal to omega Gc is equal to phi, then phase margin is equal to 180° plus phi. So try to understand. Don't get confused. I'm again recalling. So we have two terms. We have gain margin and we have phase margin, right? So again, the definition remains the same. The amount of gain required to take a system to the verge of instability. Similarly, phase margin, the amount of phase required to take the system to the verge of instability. Now, gain margin is defined as phase crossover frequency and phase margin is defined as at gain crossover frequency. So you should know what is gain crossover frequency and what is phase crossover frequency. Phase crossover frequency is that value of frequency where where the value of angle of Gj omega Hj omega is minus 180, and phase crossover frequency is that frequency where my magnitude of Gj omega H omega is unity, right? So in case of phase margin, so in case of this gain crossover frequency, if the magnitude of my transfer function at phase crossover frequency is x, then gain margin is 1 over x. Similarly, if the angle of my transfer function at gain crossover frequency is phi, then my phase margin is 180 plus phi. Right? Now I told you this thing that the amount of gain that is required to bring a system to the verge of instability. If I say my gain margin is infinite, what does it mean? If I say anyone, if I say my gain margin is infinite, what does it imply physically? If you're able to answer this question, then you have understood. So gain margin is the amount of gain that is required to take a system to the verge of instability. But I am saying gain margin of a system, let's assume if gain margin of a system is infinity, what does it mean? Anyone?
That means if you are increasing gain to any amount, the system will not be become stable, unstable.
So it means the system is always stable.
Yes, sir.
Yeah. So you have studied second order systems. So if we see second order systems or general form of second order systems, we have s square plus 2 zeta omega and s plus omega n square. And if you find the solution roots of this equation, you get these roots in terms of zeta, and then if my zeta is less than 1, I get an overdamped system. If my zeta is greater than 1, I get an, sorry, this is underdamped, and here it's overdamped. And if my zeta is equal to 1, I get critically damped. So now, if you are given my system is underdamped, you know the pole location of my system. If it is underdamped, is this. Similarly, if it is overdamped, you know the pole location is this. Similarly, if it is critically damped, you know you have a repeated poles. But every time, for all these cases, my poles lie in the left half plane. So what does it mean? It means my second order system is always stable. So if my second order system is always stable, then it means the gain margin of a second order system is infinity. So wherever you see a second order system, you should know that, okay, its gain margin will be infinity, right?
So third case is for critical dam.
Sorry.
This the third case is for critical dam.
Yes, third is for critically damped. When zeta is 1, you have a critically damped system. I think for that, you have repeated roots in the left half. Left half, not on imaginary. So, but in any case, you have a stable system. Okay, so let me see whether there are any questions.
So when gain margin is infinity, system is unstable.
No,
It will be stable. Infinity
So
means
I
positive.
said, I said, yeah. So gain margin and phase margin, if both gain margin and phase margin are positive, then we have stable systems. These things will be clear when we move ahead doing Polar, Nyquist, and Bode plots. So, so if you have a question, so if you have any other question, you can ask, or we should move forward with questions. Okay, so the question is the critical value of gain. The critical value of gain, let's assume that's kg of a system is 40, and the system is operating at a gain of 20. The system is operating at a gain of 20, where the critical value of gain is 40. So what is the gain margin? What is the gain margin? So this system is operating at this 20, then the critical value of gain is 40, right? So the critical value of gain is 40. So can anybody tell me what should be the value of gain margin based on this definition that I defined right now? So the gain margin will be this critical means this critical value means I told you if my system is critically damped here, overdamped, underdamped, and critically damped. So it means it's at the boundary. Similarly, if I'm saying it's a critical value of gain, it means it is the value of gain where my system is marginally stable, right? So this Kj is K marginal. So my gain margin is K at marginal divided by K that is its operating desire. So we have 40 over 2, my gain margin is 2. And if I'm asking you to find gain margin in decibels, what will it be? It will be 20 log of 2, which will be 6 decibels. Sometimes in options, you're only given the values in decibels. So you have to be very careful. For example, for this question, the options would have been 2 decibels, 3 decibels, 6 decibels, and 4 decibels. So you found it is 2, so you will straight away take this. But it's given in decibels, so you have to be very careful. Right, so now let's do one good question.
So gain margin is equal to K marginal upon K derived, na?
K desired, like the operating value of gain. Desire.
Okay.
Yeah, now let's do this question. This is a good question and it will clear. So the gain margin in decibels of a unity feedback control system whose open loop transfer function G of S, H of S is given as 1 over S into S plus 1 is. So you have to find the gain margin of this system. It's a unity feedback system, and where the open loop transfer function is given by this. And remember, whenever we are talking about gain margin and phase margin, we are talking of open loop transfer functions.
Sir, in previous case, answer is 6 dB, na?
Yes.
So you are tick on A.
No. Answer is 6. I was just understanding. Like. Can you solve this question? What is the gain margin? So what is the order of this system?
Second order.
So if it is second order, what is the gain margin? What What's the gain margin if it's a second order system? I right away said that the gain margin of a second order system is infinity because second order systems are always stable. But let's solve it in a proper way, whether we are getting infinity or not. So you are given GSHs. So the first of all, what you will do, you will convert into J, put S as J omega, H J omega. It will be 1 over J omega, 1 plus J omega. Okay. Now I need to find gain margin. So I told you gain margin is defined at phase crossover frequency. Phase crossover frequency. And you know, at phase crossover frequency, my angle of GJ omega, HJ omega at phase crossover frequency is equal to minus 180. Right? So now what is the angle? I have taught you this thing in the previous lecture when we were solving root locus, how to find angle of a transfer function. So can anybody tell me what should be the value of what is the angle of this transfer function? It will be
minus 90 minus tan inverse of omega by 1.
yes, minus because it's in the denominator. So then minus
Yes.
90 because j omega, there's no real term. And then we have minus tan inverse of omega. But I am putting omega at omega PC because I need to find the gain crossover frequency. And I know when I put omega as omega PC, I know the angle is 180. So what will be the value of this tan inverse of omega PC is 90 degree. It means my omega PC is, what is omega PC?
Infinity.
Infinity. But we will not stop here. What we will do, we will find the magnitude. We'll find the magnitude of GJ omega HJ omega at omega PC. Right. So what is the mod value of GJ omega HJ omega? It is 1 over omega divided by omega square plus 1. So I did nothing. I just took omega square, that stands cancelled with square root, and omega square plus 1. Now, if you put, so I told you, so this is magnitude. So this is magnitude. And when we put omega as omega infinity, it will be 0. Right? So then gain margin is what? Gain margin is 1 over magnitude. 1 over magnitude means gain margin is infinity. I hope this is clear. So if this is clear, please solve this question. The open loop transfer function of a unity feedback control system is given by G of S is equal to 150 divided by S into S plus 9 into S plus 25. Find the gain margin. Please try to solve, everyone. I'm giving you a hint. So for gain margin, you need to find phase crossover frequency, and at phase crossover frequency, you know the angle is minus 180. Then you'll get the value of omega PC, that's phase crossover frequency, and then you'll find the magnitude of GJ omega Hj omega at phase crossover frequency, and then take the reciprocal of that. Anybody? I'm writing, making it easier for you. Now, please solve. I have given you a hint.
Which is A and B.
Sorry?
Which is A and B.
So you need to identify that from the question. I wrote this formula to make your calculations easier, because when you will find phase crossover frequency, somewhere you will be having, you'll be needing this identity. We'll get tan inverse A plus tan inverse B somewhere, and then to solve that, I wrote the formula. You need to put in the values, you need to find the values yourself. Should I solve it?
Yes, sir.
Okay, let me solve it. So we have to find gain margin. We should go step by step. So in order for us to find gain margin, we should know what is my phase crossover frequency. So I know my phase crossover frequency, the angle of GJ omega HJ omega at phase crossover frequency is minus 180, right? And now you need to write the angle. You need to write the angle. So what I will do, I'll write it like this: GJ omega is equal to 150 divided by J omega plus 9 into J omega plus 25, right? So what will be the angle of GJ omega? angle of GJ omega will be minus 90 degree minus tan inverse of omega by 9 minus tan inverse of omega by 25, right? So because the angles are in the terms are in denominator, that's why minus. Now I know when my omega is omega phase crossover frequency, then my angle is, then this is 180 minus 180. So I'll put omega as omega PC. So it will be minus 90 degree minus tan inverse of omega PC over 9 minus tan inverse of omega PC over 25 is equal to minus 180. Or if I take this 90 this side and cancel the negative sign, you will get tan inverse of omega PC over 9 plus tan inverse of omega PC over 25 is equal to 90 degree. And then I have given you the formula for tan inverse of A plus tan inverse of B. And I'm just making use of that formula. So it will be tan inverse of omega PC over 9 plus omega PC over 25 divided by 1 minus omega square PC divided by 225. And this is equal to 90 degree. If we simplify it, we will get 1 minus omega square PC divided by 225 is equal to 0. It means omega PC is equal to 15. So now I got the value of phase crossover frequency. Now at this frequency, I need to find the magnitude, right? So I'll just put for the magnitude of GJ omega at omega is equal to phase crossover frequency, and which is equal to 15. If I put the values, it will be 150 over 15 into under root of 306 into under root of 850, which is equal to 0.0196. I directly skipped the calculation because you just have to take the magnitude. It's very simple. Now I got the magnitude. I know the gain margin. Gain margin is 1 over this magnitude. It's equal to, I'll directly write it in decibels. So it will be 20 log of 1 over 0.0196, which will be 34.1 decibel. Right? So basically, whenever you have to find gain margin, you have to first understand that gain margin is found at phase crossover frequency. And at phase crossover frequency, my angle is minus 180. So making use of these two conditions, you should be able to find the phase crossover frequency, this gain margin. Now, very, 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 very important and conceptual.
I have one doubt, sir. The formula
Yeah.
tan inverse of that some term divided by that. So we
Uh,
have equate the denominator equal to 0. That I didn't get.
no, not okay. Wait, here.
Yeah, yes, yes.
So
Here
see,
this.
we have
That is
this
one
whole
bracket, tan
term.
inverse of one bracket.
Yeah, it's one bracket.
It's one bracket.
Is that fine?
Yes, sir. Yes.
No, if that is not clear, I'll still like clear it. So,
Not
so
clear, sir.
this, yeah, this
So
thing.
if you can
So
draw
in
one bracket
yeah,
for numerator denominator on both sides, then it will be less.
exactly.
Yes.
So if you take tan here, it will be this whole
Yes.
is equal to tan 90, and tan 90 is
Tan 90 is 0.
tan 90 is infinity.
Infinity. Tan 90 is infinity.
Yeah. then when you solve it, so you have okay, I'll solve it. So you have, okay, I'm solving it here only. So you have omega PC by 9 plus omega PC by 25 divided by 1 minus omega square PC by 225 is equal to tan 90, and tan 90 is infinity. So I'll write infinity. So it means this term is infinity. How
Zero.
this will become infinity? When this is 0. So
Denominator
when
is
this
zero.
is 0, that's why I have to write.
Yes, yes, yes. Thank you, sir.
Okay. Yeah. Okay. So now this is very important and conceptual question. I'm writing it. The open loop
20, so
freak.
20 log of 1 upon magnitude is equal to gain margin. Na? 20 log of 1
Yeah.
upon
Yeah. Magnitude.
magnitude.
Yes. It's either 1 over magnitude. Then I am writing it in decibels. That's why I have written 20 log.
Yes, sir. Yes.
Right. So this 1 over, this is actually gain margin value, absolute value. Then in decibels, you're finding this. Okay. So the open loop frequency response, the open loop frequency response of a system, okay, I'm writing it, of a system at two, this is the last question. So if you're able to understand it and solve this, then phase margin and gain margin stuff is understood. So the open loop frequency response of a system at two particular frequencies, at two particular frequencies are given by. So we have 1.2 angle minus 180 degree and 1.0 angle minus 190 degree. Then it's asked the closed loop unity feedback system. The closed loop unity feedback system is then. So is it stable, marginally stable, or unstable? So I told you, I'll give you a hint. I told you if my gain margin is positive, my system is stable. So is with the phase margin. So if my both gain margin and phase margin are stable, are positive, my system is stable. If they both are negative, my system is unstable. So now what is given in the question? So you have to understand. You have to understand from the question the concepts. I'll try to help you. So one response is given as 1.2 angle minus 180, and another response is given 1.0 angle minus 190. I told you again. So we are doing questions on phase margin and gain margin. So obviously it's about phase. So obviously it's about gain margin and phase margin, this question. So it's easier this time, but it might not be when you are solving questions in general. So I told you that when we talk of gain margin, we talk of gain phase crossover frequency. And when we talk of phase margin, we talk of gain crossover frequency. And my phase crossover frequency is the value of frequency at which the angle is minus 180 degree. So we have angle is given as minus 180 degree, right? So when my angle is minus 180 degree, so this is my phase crossover frequency and the magnitude at this angle. So and the magnitude when my angle is 180 degrees given as, so I can write magnitude of GH is equal to 1, 2. And I told you the gain margin is what? 1 over the magnitude of GH at omega equal to omega GC, right? So it's nothing but 1 over 1.2, because directly we are given that it's at minus 180. So the magnitude is given, everything is calculated. Is it clear? So in decibels, you will calculate gain margin as 20 log of 1 over 1.2, which is equal to minus 1.6 decibels. Right? So similarly, can you come up for the other can you come up with a conclusion for this part? So you are given 1.0 and angle is minus 190, and your given magnitude is given as 1. You know, when the magnitude is 1, the value of frequency when the magnitude is 1 is called phase crossover frequency. Sorry, yeah, gain
Right.
crossover frequency. So it means, what is gain crossover frequency here? Minus 190 degree, right? So if my gain crossover frequency is minus 190, then phase margin is what? 180 minus 190 degree, which is equal to minus 10 degree. It means since both gain margin,
Gain crossover frequency should be in radians. Huh? Gain
yeah,
crossover frequency. Here you are
uh,
writing WGC is equal to minus 190. That is, I think at gain crossover frequency, phase is minus 190, as you want to say.
yes.
Phase angle should be minus 180. Na, barabar, na? It is WGC is equal
So
to minus 190.
okay, so you are talking about this.
This one is magnitude, minus 90 is phase contribution.
Yes.
So at which
So
frequency?
yes, exactly. So I said when I was explaining gain crossover frequency, I said gain crossover frequency is that frequency when my magnitude is unity.
Yes,
So my magnitude is unity.
yes.
So then what is this angle?
That is for phase barabar. Phase contribution will be minus 90 at 1 degree when the magnitude is 1.
Yes, when magnitude is 1, the angle is so I when I defined here, if you see, when I defined yeah, when I defined phase margin, what I said you need to find gain crossover frequency. And what is gain crossover frequency? Is the value of frequency when the magnitude is unity,
Yes,
right?
yes.
So when my magnitude is unity, I'm given the angle is,
Minus 190.
so that minus 190 is my gain crossover frequency,
Yes. So phase margin will be
right? So
negative. Hence system will be unstable.
yes,
Yes.
yeah, right. So, are you attending our session for the first time, or you have attended past sessions as well, Yogesh?
No, sir. I am attending it first time. This session.
Yeah.
Yes, sir, yes, sir.
But have you like seen the past videos which were
Yes,
shared,
sir.
or
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
and can you please like introduce yourself? What are you doing right now? Like
So
teaching some?
presently, yes, sir, myself is Yogesh Anga. I am working as a teacher in JSPM's Bhirabai Sawant Institute College, Wagholi, Pune. So I am,
Okay.
yes, sir, yes, sir.
So you have
Basically,
been in this field for how many years?
I spent almost 15 years in teaching.
Okay. Okay.
Yes, sir. But
So
right now I am
you
contributing for control system. Presently, I am contributing for control system subject.
okay? So in electrical
I am basically from
engineering.
instrumentation. Instrumentation.
Okay, you're from instrumentation. Fine.
Yes, sir, yes, sir, yes, sir.
Okay, so are these things clear to others as well? So, like, should we move forwards? We have some other
Yes,
stuff
sir, yes, sir. Yes, sir, yes,
as
sir. We
well.
can. Yes, sir.
Okay, so now let's talk about polar plots. So when we talked about root locus, I made it very clear that how we should find angle of a complex number based on quadrant. So that concept will be used here. right? So if you have an open loop transfer function,
Sir,
so
what is the answer
G,
for previous examples? It is unstable. Huh?
yes, it's unstable
Okay,
because
fine.
both are negative. It's
Yes, yes.
unstable. So whenever we talk of these polar plots, so we talk of open loop transfer functions. So whenever we have open loop transfer function, so if we are plotting this Gj omega Hj omega, right? So if we are plotting the magnitude versus the phase angle, uh, as we vary the frequency, I told you we are doing frequency domain analysis. So uh, as we vary frequency, for example, this is real part of g of h. This is imaginary part of g of h. So as we vary frequency from 0 to infinity, how my plot looks like in this plane is called a polar plot, right? So as I vary frequency from 0 to infinity, so with frequency variation, how my this Gj omega Hj omega, uh, like how it comes out, how the plot comes out in the plane of real part of Gj omega and imaginary part of Gj omega is given by polar plots. I'll explain it uh, like in the form of examples. For example, if we take this example, G of s, h of s is equal to 1 divided by 1 plus st. Can you tell me what is the order of this system and what is the type of this system? I have
Order is
Type
first
zero,
and type is
Uh,
type
1.
zero first order.
type is on type
yeah,
is
so
on
it's
order
Type zero
is
first order.
type 0, order
order
First.
1,
of one.
right? So I have taken example of a type 0 and order 1 system, right? So whenever you have to make polar plots, so the first thing is we replace this s with j omega, right? So I will write gj omega hj omega. Why? Because I need to vary omega only, j omega tau, right? Then what I said, I need magnitude as well as phase because I am plotting phase and magnitude with respect to frequency. So can you tell me what is the magnitude of this? G, I'm writing it like this, Gj omega. So the magnitude will be 1 over under root of 1
Means
plus omega
Plus
omega
square
t
t
upon
omega
t.
square,
square t square.
right? And what should be the angle of Gh omega?
9 90
Min-
minus
No, not 90. How 90?
minus tan inverse of omega t by 1.
Yes, it will be minus tan inverse omega t, right? So we have magnitude, we have phase. Now what I said, we need to vary omega from 0 to infinity and see how this plot will look like. So I have omega, I have magnitude, and I have phase. When my omega is 0 and when my omega is infinity, I need to find the value of magnitude. So if you put omega as 0 in magnitude, what should we get?
1.
1. Nice. And if we put omega here, so tan of 0, what is tan of 0?
0.
0. So you'll get tan of 0 here. And then if I put if I put omega as infinity, what should I get?
0. Magnitude 0.
0, 0
phase.
here. So if I put then omega as infinity, what should I get?
Minus 90.
Minus 90.
90, minus 90 degree. Right. So okay, let's then plot it. So we have real part, we have imaginary part. So you know this is clockwise we are taking negative angle and counterclockwise we are taking positive angle. So I have explained it in the last lecture as well. So when my magnitude is 1, my angle is 0. So my angle is 0 means this line, right? So my angle is 0 means this line, and my angle is plus 90 means this line. My angle is plus 180 means this line, plus 270 means this line. So if I go like this, then it's positive. And if I go like this, then it will be negative, means this will be minus 90 degree. This will be minus 180, minus 270. I hope that is clear already from the previous lecture. So let me use a different color. So it's 0 degree, but my magnitude is 1. So let's assume this is that point, where 1. So at omega equal to 0, I'm here. Then as omega goes to infinity, my magnitude is going to 0. So my magnitude will be here, but my angle will be minus 90. And if I take another value, if I take omega equal to, if I take omega equal to 1 over t, I'll get magnitude as 1 over root 2 and angle as minus 45 degree. So if I take omega, if I take another point, which is at omega is 1 over t, that is somewhere in between, I get 1 over root 2, but minus 145. Minus 145 is somewhere here, right? So, okay, wait. And then when I take omega as infinity, my magnitude is going to 0. So I'm moving something like this. Right? So this is omega equals to infinity, right? So this means as I traverse from omega equal to 0 to omega equal to infinity, I'm getting a plot like this. This is the polar plot of this type 0 and order 1 system, right? So this is how my omega and magnitude is varying with respect to, sorry, my phase and magnitude is varying with respect to omega. Now let's take another example. Now this time, if I'm writing a system like this, g of s, h of s is equal to 1 over s into 1 plus st. So what is the type and order?
Type 1 order 2.
Nice. This is type 1 order 2. So I've just like increased type as well as order. Okay, so now whenever we have to draw polar plots, how do we start? We take gj omega, hj omega, replace,
J omega
yeah, 1
into
plus
1
j,
plus J omega t.
yeah, thank you. Now what we will do, we'll find the magnitude.
Magnitude of
Magnitude of jj omega, hj omega, which is equal to 1 over,
by omega root of 1 plus omega square t square.
yes. Similarly, what will be angle of gj omega?
90 degree minus
Minus 90. Minus 90.
Yes, minus
Minus
90.
90 minus j
minus
omega,
tan inverse of
omega by
omega.
omega t.
Is it clear? Right. Now again, let's make a table. Let's make a table. We have omega, magnitude, and phase. So can you tell me when I put omega equal to 0, what is the magnitude I'll get?
Infinity.
Infinity. And what will be the phase?
Minus 90.
Yeah. Similarly, when I put omega equal to infinity, my
Magnitude will be
magnitude
0.
will be 0 and my
0.
phase will be
Minus
minus
90.
180,
Because of
right?
the two poles, it will get added. Minus 90.
Yeah. It's actually like that. So it's real. It's imaginary. So at where I'm at, when omega is 0, my magnitude is infinity. So my magnitude is infinity means and angle is minus 90. So at this line, I'm at the infinity, right? So I'll start somewhere here from infinity. And then as my omega tends to infinity, my magnitude comes to 0. So I will converge here, right? And but angle is minus 180. So it will be something like this.
Ito. Hindu. Kami ko.
Someone has kept mic on.
Mhm.
Someone kept his mic on. Some disturbances we are getting.
Yeah, I'll just mute it. Is it fine now?
Yes, sir.
Okay.
Yes, sir.
So we got polar plot like this, right? So this is minus 180 here if we go like this. So now without like there is a pattern. So if you can see, I started with type 0 and order 1 system. I was in quadrant 4. Then I started with type 1 and order 2. I am in quadrant 3. So in general, I'm making a table which will help you drawing a polar plot, approximate polar plot, not exactly, but approximate polar plot you can draw based on this table, like this generalized. I'll make this diagram. So quadrant of polar plot. So if you are solving multiple choice questions, you'll be able to solve those in few seconds by making use of this table. Right? So you have real part, you have imaginary part. Oh, sorry, I forgot to mention one thing. This polar plot, the starting point is called tail, and the end point is called head. Right? So similarly, I'll write it here.
Sir, explain graph, sir.
Sorry.
Explain graph.
Yeah, give me 1 minute. I'll explain again.
Yes, okay, sir.
Just let me make it. So now see, I made a generalized diagram. So where if you have a type 0 and order 1 system, your polar plot will start from fourth quadrant. I'll write it as 1, 2, 3, and 4. So if you have a type 0 and order 1 system, as we saw here, we had a type 1 and we had a type 0 and order 1 system. So my polar plot will start in fourth quadrant and even terminate in fourth quadrant as well. So it will start and terminate in the same quadrant. So if I have a type 0 and order 2 system, it will start in quadrant 4 and terminate in quadrant 3, right? So similarly, if I have type 1 and order 3, which is the most asked transfer function, is type 1 and order 3. So in that case, you will start. So for example, if I have to make it, it will be something like this, right? So I start from quadrant 3 and I end in quadrant 2. So if I have a type 1 but order 3 transfer function, then I have polar plot something like this. And what is a type 1 order 3 transfer function look like? It is something like this: s into s plus 1 into s plus 2. So if you have a transfer function like this, then your polar plot will be something like this, right? So it's very easy.
Like
So
like
anybody has any doubt?
explain graph, sir.
Which graph?
Second problem in
Okay,
the
okay, okay,
polar graph.
okay, fine. So this graph.
Yes, sir.
So this is by type 1 and order 2 system, where I have to draw a polar plot, right? So in polar plot, what do? We draw the magnitude and phase of gj omega hj omega with respect to frequency. As we vary omega from 0 to infinity, we see the relationship between magnitude and phase and plot that. So I have calculated magnitude here. I have calculated magnitude here and phase here. Then I put omega. Then I will vary omega from 0 to infinity. When I put omega 0 in magnitude, I'll get infinity. Why? Because it will be 1 over 0. So it will be infinity. Similarly, my phase will be tan minus 90 minus tan inverse of 0. Tan inverse of 0 is 0. So I'll get minus 90. Then when I put omega equal to infinity, I'll get magnitude as 0. Why 0? Because in omega is a very, very huge number, infinity, and 1 divided by very, very huge number is a very, very small value. So when it's infinity, it will be very small, so it will be 0. Then here, tan inverse of my omega t, when it's infinity, means it's 90. So minus 90 minus 90 is minus 180. Then I have plotted it here. So when I had omega equal to 0, I have magnitude as infinity. So this is infinity, right? I'm plotting it like this. Then as I increase my frequency to infinity, my magnitude is converging to 0. So my magnitude is converging to 0. But when my magnitude is 0, I have angle minus 180. So it's measuring from here, minus 180, right? So is it clear now?
Yes, sir.
Okay, thank you. So now, anybody has
These
any
videos will
problem?
be available, na? Recorded videos will be available. This particular
Sorry,
session.
sorry.
This recorded video will be available, na? Recording of
Yes,
this
yes, yes,
session.
yes,
Yes.
yes, yes, yes. It will be available. So now, but remember, when I've given this table, I have assumed this general form. You have there is no pole, there is no 0 in the transfer function, and there is no pole in the right half plane. So whenever there is no pole in the right half plane or no 0 in the transfer function, then you can use this approximation, right? But what if you have sometimes when you have a problem like this? For example, so first let's try to sketch polar plot 1 over s square into 1 plus s into 1 plus 2s. Now, can you try? Can you try solving this question?
Order two.
Sorry.
Order 2, type 4.
Okay, so now can you find the magnitude and omega? So how should how should a type 2 and order 4 polar plot look like? It should be order type 2, so it should come from here, and order 4, it should be something like this. Is it clear? So you will try this, and you should get something like this because it's type 2 and order 4. So, and it's a generalized form. There is no pole in the right half plane. There is no zero. So we can make use of that table, that generalized graph, and you'll get a polar plot like this. You'll definitely try it. But what if you have some question like this? S plus 2 divided by S plus 1 into S minus 1. Please try to solve it. This is your transfer function, open loop transfer function. Now you cannot apply that table. Why? Because there is a 0 as well as you have a pole in the right half plane. So you cannot apply that table which I showed you right now.
Sir,
Yes, yes.
in the open loop transfer function given over here, if we find out there is one pole at right hand side of this plane, so
Yes.
directly can we comment system is unstable?
I'm not asking you whether system is stable or unstable. I'm asking you to draw the polar plot.
Yes, sir, we will draw.
One more thing. You are saying one pole is in the right half plane, but this is open loop transfer function.
Yes, open loop.
When we comment whether my system is stable or unstable, we look at the closed loop transfer function, not open loop transfer function. So
Yes,
maybe
yes.
the closed loop transfer function is stable, but
Yes,
open
sir.
loop transfer function is not. So first of all, I will write it in time constant form, right? So do you know what is time constant form of transfer function?
K into 1 plus st, 1 plus
Yes.
st, 1 plus st at
So
numerator divided by
whatever,
s st.
yeah, whatever I write 1 plus s, right?
Yes,
There is
yes.
like here it is 2. I'll just make it 1. So
Yes,
when
sir.
I do that, so I'm writing it in time constant form. So let's do it. So it will be if I'm writing it my time constant form, it will be 2 into 1 plus 0.5 into s divided by s plus 1, or I'll write it this way. Sorry. Yeah, I'll write it 1 plus s into, if I'm writing 1 minus s, then there will be 1 minus outside because everything I have to write 1 minus s, 1 plus s. 1 is 1 I have to write first, then there will be 1 minus.
Minus we have to take common. है ना?
Yeah, why? Because we are writing in time constant form, then
Yes,
everything
sir.
has to be written like 1 plus s, 1 minus s, whatever. So now put j omega. I told you whenever we have to make a polar plot, we put j omega. So when I put j omega, it will be minus 2, 1 plus 0.5 j omega divided by 1 plus j omega, 1 minus j omega. Correct? So now it's
Yes.
very simple for us. We'll take magnitude. I will directly write the magnitude. Magnitude will be 2 into under root of 1 plus 0.5 omega square
divided
divided
by
by
root of 1 plus
1
omega square.
whole square. That will get cancelled.
Okay.
Okay?
Okay. Okay.
Yeah. Similarly, we have angle of gj omega, which is equal to minus 180 plus tan inverse of, yes,
1 minus j omega
yes.
root of
We are writing
180.
magnitude.
Okay.
We are writing magnitude, right? So uh, there is no minus in magnitude, right? There is magnitude of a. If we have a plus ij, so the magnitude will directly write a square plus b square under root of. Is that clear?
Okay.
Okay, so if the angle is this, then what we have to do, we have to put in the value of omega as 0 and then the value of omega as infinity. So when you put omega as 0, my magnitude will be 2, and
So
angle of
here
GJ.
in phase
Uh-huh,
calculation,
uh-huh.
you have written minus 180.
Yes.
So minus tan inverse of omega by 1.
See, yes. So you can write directly tan inverse of 0.5 over 0.5 omega by 1, this term,
No,
right?
for denominator I am asking. Denominator tan
Yes.
inverse
So
omega by
I'm
1.
coming. So it will be, so first term will be this, then second term will be minus of tan inverse of omega by 1, right? Then
Yes.
if you see, this is in second quadrant. So if it is in second quadrant, I'll write it as 180-degree tan inverse of omega by 1. So omega by 1 and this omega by 1 stands cancelled. That's why this minus 180 will come up.
Okay.
Is it clear?
Yes, sir.
So, okay, so where were I? So I was here. So the magnitude will be, similarly, when we put omega as infinity, my magnitude will be 0, and my angle of GJ omega will be minus 90. And if I have to plot it, so at omega equal to 0, my magnitude is 2. My magnitude is 2, right? But an angle is minus 180. And similarly, as it starts decreasing, so I'll get something. Right, so you check it. I've directly written the values. You check it, the calculations yourself, and accordingly you can draw. Right. So we have very less time left, and we have to cover Nyquist plot as well as Bore plot. So quickly, I'll go to Nyquist plot. So you have understood. If you have understood polar plot, then Nyquist plot can be drawn from polar plot only. Right. So what you have to do. So quickly, I'll do 1-2 questions on Nyquist plot. So if you have to make a Nyquist plot, what you will do, you will make a polar plot, plus you will make inverse polar plot, plus you will make infinite semicircle. I'll tell you what is this, where infinite semicircle is given by type of GH, and inverse polar plot is equal to mirror image of polar plot about real axis. Okay, so if you have to make a Nyquist plot, you will make polar plot, then inverse polar plot, and then you will make an infinite semicircle, which is given by where how many number of semicircles you have to make, that is given by the type of GH. Well, this will be explained from some problems. Let's take a problem. If we have been asked to draw Nyquist plot for the following transfer function. right? So there is no zero uh, in the transfer function. There is no pole in the right half. So whatever we have learned, that's applicable. That's applicable here. So if I have to make this is real part of GH, this is imaginary part of GH, right? So now this is now can anybody tell me what is the type and order?
Type 0.
Uh, and order 2.
Type 0 order 2.
Right. So if it is type 0 order 2, my polar plot will start from here and end at here from that table. Right. So that's what I'll make. So I'll make approximate polar plot. It will be something like this. Right. So my polar plot will be something like this. Okay, so now I have to make inverse polar plot. So I told you for Nike, in order for me to draw inverse Nyquist plot, I need to draw polar plot, inverse polar plot, and one infinite semicircle, which is given by the type of the system. So now you have to draw mirror image along the real axis. So this is my real axis. So I need to draw mirror image of this polar plot. So it will be like this. Right? So this will be mirror image of this polar plot. So we drew polar plot, inverse polar plot of this system, right? Now we have to draw one infinite semicircle. So, but the system is of type 0. So there will be no infinite semicircle in this plot. So this is my Nyquist plot. So have you understood? Anybody has any doubt?
No, sir.
So I drew polar plot. I drew my inverse polar plot, and there was type is 0. So I did not draw any infinite semicircle.
Sir, why
Yes.
type 0 not infinite semicircle is allowed loaded?
Why? Why?
No, there is no pole at origin.
Type 0, why infinite semicircle is not allowed?
I'm not able to understand why something is not allowed.
Infinite
Why
semicircle.
you are not drawn semicircle in type 0 system? That is her question. His question.
Yes.
Okay. Like there are answers because we are just approximating it, right? So in when you have type 0 system or type 1 system, this is a way of drawing it, Nyquist criteria. There are other ways. If we see that, maybe then things are more clear why there is no infinite semicircle for a type 0 system. So we'll have to check. It's maybe because there is no pole at the origin, but again, I'm not sure.
This part is getting closed. When it is going to polar plot, it is getting closed at second quadrant at origin. And then
Yes.
if you start from that place, it will close at the end. So end to end closing is possible in the same inverse and polar plot and inverse polar plot. That's why semicircle is not needed. Semicircle will be needed only when there is not getting closed. I think it is the answer. I think.
When it's not closed.
Yes. Now, sir, if you are plotting polar plot from this from as per our usual practice, and when you are
Mhm.
again plotting inverse polar plot, isn't
Mhm.
it? So it will become symmetric at the real axis. And if you
It
start
is.
from the polar plot, from the original polar plot, ending
It's
at
it's
origin in the second quadrant, again you are starting from the second quadrant and you are ending at the first quadrant. So
okay.
it is continuing the close path. It is continuing the close path. So there is
Okay.
no need to join it by the semicircle. Semicircle is used to join, I think.
Okay.
Uh,
But by your logic, again, I'm
yes.
not sure about it. But if we can try from your logic, this question,
Okay.
10
Let,
over
let us give
S.
it a try then.
I'm just giving a pole at origin. for the same
Yes, sir.
system. So
Yes, yes,
so if now this is type 0, sorry, this is
yes.
type
Type 1.
1 and order 3.
Yes,
So it will be something like this. Let me make it. Yeah. So if it is type 1, so it will start from here, and it's order 3. So it will be something like this. Wait. Is it clear?
yes,
This is
sir.
polar plot. And if I have to draw inverse polar plot, that will be something like this,
Yes,
right? So something like this. But we have type, yeah, he was correct.
yeah, yes, sir. Now we have to close it from that
Yeah,
end to
now we
this
have
end.
to close it. Yeah. So now we have to close it, and so yeah, there will be one infinite semicircle given by this. So
Yes,
that will be
yes. Your original plot is starting point, and image plot, image of polar plot is your ending point. We have to join
yeah,
from that ending point to starting point.
yeah.
So
So
this semicircle now.
huh?
Sir, only you are only given now where semicircle will be equal to type of system. If there is
Yes.
type 0 system, then and then only because you written and I only thought on that.
So it's type 1.
Yes, it is a type 1 system.
There will
When
be
there is
one
a pole at
semicircle.
origin, then we have to draw
Yes.
this semicircle.
Yes.
Yes, sir. We
Okay.
can
So
try
is
by
this
other
correct?
one. Yes, sir. Yes, sir.
So is it clear to others?
Sir, what about the encirclement?
Yes. So that is about the stability. So okay. Let's check that as well. So now, if we have to check whether my system is stable or not from Nyquist plot, so what we do, we find the number of encirclements n, right? So we find the number of encirclements n, which is equal to p minus z, where p is the number of open loop poles that are in the right half plane, right? So p is the number of open loop poles in the right half plane, and z is the closed loop poles in the RHP. So if Z is closed loop poles, can I say Z is the number of open loop zeros?
Hmm, नहीं बोल सकते ना सर ऐसा.
Because if we see root locus, we are say if we are taking open loop transfer function, and we are starting from poles and we are terminating at zeros. When I start from poles, my k is 0, and I terminate at infinity. When k is infinity, I terminate at 0. And this is my open loop system. And when I'm terminating, I'm getting a closed loop system. So my
Hmm.
poles, my open loop poles, eventually, when my k is changing, when I'm getting a closed loop response, then my open loop zeros become closed loop poles. Okay, so no problem at all. This is correct. So my Z is the closed loop pole. So now I told you, whenever I have to check the stability of a system, I take closed loop transfer function and find the number of poles in right half plane. If I have one or even more than one poles in the right half plane, then my system is unstable, right? So this Z is giving those closed loop poles. So if I know the number of open loop poles from the transfer function, I can find the number of encirclements, but this number of encirclements are around the point -1 plus J0. So this is about the point -1 plus J0. So let's try to apply this concept for this question. So given this question, we have we have two open loop poles which are at -2 and -4. So for example, if this is -2, this is -4, right? And this is my origin 0. Okay, so my P is 0. So in here, my P is 0 because no pole is in the right half plane. Now I will see my encirclement after I draw Nyquist plot, encirclement of this -1 point. So there is no encirclement for this -1 plus J0 point. It means my n is 0. So
Zero.
when my n is 0, P is 0, what is the value of Z? 0, right? So if there are no encirclements, then my system is, it means there is the number of closed loop holes in the RHP is 0. It means my system is stable. So this is a stable system.
If the encirclements are present, then system may be unstable.
Yes, but again, we have to satisfy this condition.
Okay.
Right. We have to see how, obviously, if encirclements are present, there the system is unstable. But again, then we have to see if we are asked to how many closed loop poles are lying in the right half plane.
Mm-hmm.
You can also check that from Route's criteria. But in Route's
Encirclement
criteria,
we
you are
can find out only after plotting the Nyquist plot, na?
exactly. So
So we
when
can't
you are
find
when
out encirclement just by formula or by putting value n is equal to p by z. We have to first of all
yeah.
plot the Nyquist plot.
Exactly. So first of all, we have to see the open loop transfer function. From open loop transfer function, we'll get the value of P. Then we will draw a polar plot and then inverse polar plot and then the infinite semicircle. So when we are done, we'll get the number of encirclements. So when we get number of encirclements, then we can find the value of Z. So if Z is positive, then the system is unstable because there is at least one pole in the right half plane which is making my system unstable. So the same thing we do in Route's criteria, but in Route's criteria, we are directly given a closed loop system. But here
Yes.
we are given an open loop system. So it's a bit easier. And it's in Route's criteria, if we have a huge system, so it will be very difficult. The calculation becomes tough. Right. So there are few terms like what are minimum phase and non-minimum phase transfer functions, right? So for example, a minimum phase transfer function is a transfer function whose all poles and zeros lie in the left half plane, right? Similarly, non-minimum phase transfer function is that transfer function whose at least one pole and zero lies in the RHP. So you should try to learn these concepts like these terminologies because they will be very helpful in future. But before I end, we should try at least one question on Bode plots because I have not touched Bode plots and there are questions on Bode plots in your assignment. So when we started this lecture, I told you that we are plotting magnitude as well as phase with respect to we are plotting magnitude as well as phase with respect to frequency. Now, when we are plotting this, then we derived some formulas for the magnitude as well as phase, right? So when uh, it's actually very tough to calculate that magnitude and phase for different values and exact curves. So what we do, we make an approximate curve of that, and by taking the magnitude in decibels and plotting that with respect to frequency. And frequency, we are taking in log axis to cover like large variation. For example, uh, if we are varying frequency from 50 hertz to 100 hertz, or normally we vary frequency variation is we vary till 10 to the power 6 megahertz, right? So that's not easy to cover in a normal plot. So what we do, we make Bode plots. In Bode plots, we plot magnitude in decibels, right? And with respect to omega, which we are taking in the log axis, log scale, right? So whenever you are given a magnitude, in order for you to compute magnitude in uh, decibels, you need to multiply that with 20 log, right? So directly, let's do a question, and then maybe things will be easier for you if you practice more questions. So Let's assume you are given g of s h of s is equal to 5 into s plus 20 into s plus 50 divided by s plus 10 into s plus 100. And we are asked to draw the Bode plot for this system, right? So we need to plot magnitude as well as phase with respect to frequency. So first of all, what you will do, you will make the system in time constant form, right? So I told you everything you have to write 1 plus s form, right? So so writing it in time constant form, I'll directly write, you'll get something like this. And then I'll also put gj omega hj omega. So you will in general get it like this 5 into 1 plus j omega by 20 into 1 plus j omega by 50 into 1 plus j omega by 10 into 1 plus j omega by 100. Right? So first of all, what you have to do, you have to write the given open loop transfer function in time constant form by taking some factors common, right? And then putting s equal to j omega. Then whatever term you are getting in denominator like this, in this form, whatever term you are getting in the denominator, they are called as corner frequencies, right? So in this form, whatever terms you are getting in the denominator, they are corner frequencies. So what are corner frequencies here? I'll write them. They are 20, 50, 10, and 100. And I'll write them in the increasing order. It will be 10, 20, 50, 100. So what are these corner frequencies? If you know, when we draw Bode plots, we have poles and zeros in a transfer function. If we have a pole at origin, right, that gives you, yeah, or if you have a pole in general, that gives you a slope of 20 dB per decade. And if you have a zero in the transfer function, sorry, pole gives you a slope of minus 20 dB per decade. And if you have a zero, that gives you a slope of minus 20 dB per decade. Right. So first of all, what you do, you find the time constant form of the transfer function, then you identify corner frequencies, then you move step by step. So what you do, because the graph will be something like this. The graph will be something like this. So this will be magnitude in decibels, and this will be omega. Then again we will have phase, then we will have omega. So then you have corner frequencies, for example, 10, 20, 50, and 100. So these corner frequencies are the frequencies where my slope will be changing. So that's why. So first region you will be covering is this region. So you'll take omega less than 10, then you will take omega 10 to 20, 20 to 50, and 50 to 100. Why? Because the slope only changes when you are at these corner frequencies. Otherwise, the slope remains constant, right? So you have this gj omega hj omega. Based on this, I will proceed. So my first case is omega is less than 10. So this area, this is my first part. Like, how will my magnitude vary with respect to omega in this region when I am between 0 to 10, when my omega is between 0 to 10. So what you do whenever, so see what you do. You will put this, you will now go to this main transfer function and see. You will ignore omega in all terms. Why? So for example, you are in this region. So you will ignore all omegas here. So you'll ignore this omega, this omega, this omega, this omega. Then when you reach this point, 10 point, so you will ignore all omegas that are after 10, and you will ignore all ones, this one, which are below this 10. So for example, I'm just solving it for you. I said whenever you are at corner frequency 10, when I wrote it in increasing order, you will ignore all omegas that are present uh, uh, like all the omega terms you will ignore. So what will be my magnitude? So my magnitude will be 5 into, you will ignore all omega terms. It will be 1 into 1 into 1 into 1, right? So it will be 1, 1 into 1 into 1. It will be 5. My magnitude will be 5, and my magnitude in decibels will be 20 log of 5. Okay, now you reach this point at omega equal to 10, and you know when I'm at 10, my slope will change, right? So you started with a constant magnitude of 20 log 5 till omega is 10. So now let's come to this region when my omega is between 10 and 20, right? So this region. Now I know my slope will change. So what will be my GH? My GH will be 5. I need to ignore all omegas which are greater than 10. So I'll ignore this omega, this omega, this omega, but not this omega, right? So I'll ignore this will be 1 into 1, but I will not ignore this omega, which is at 10 because it lies between 10 to 20, but it should be less than the upper frequency. So it should be less than 20. So I'm ignoring all the frequencies, but I'm not ignoring this j omega by 10. Here I'm ignoring this one, right? So you have to remember this. So here I will write j omega over 10 into 1. So what will be my GH? My GH will be 50 over j omega, and my magnitude will be in dBs 20 log of 50 over j omega. Sorry, not right omega here. Right, 50 over omega, and it will be equal to 20 log 50 minus 20 log of omega, right? So at 20, at this 10, at 10 you have a pole, so at 10 you have a pole. So whenever you have a pole, you have the contribution to slope is minus 20 dB per decade. So at this 10, so now my slope will be so yeah, this is my magnitude now. Then again, for third region, which is 20 is less than omega is less than 50, you ignore you ignore you ignore this 50, you ignore this 100, but you will not ignore this 20, you will not ignore this 10, right? And what you will get, you will get magnitude as 5 into j omega by 20 into 1 divided by j omega by 10 into 1, which is equal to 2.5, and magnitude in decibels will be 20 log of 2.5, right? So again, you have a zero, so your slope will be 0. You already have slope of minus 20 dB per decade. Now you reached 20. At 20 you have a 0, which gives a slope of plus 20 dB per decade. So minus 20 plus 20, you'll get 0 dB per decade slope till omega is 50 is reached, right? Similarly, you will move from omega, when omega is between 50 and 100, you will get magnitude as, here what you will do, you will ignore all the frequencies, you will ignore all the omega terms except this 100, right? So then what you will get, you'll get magnitude as, directly I'll write, you'll get magnitude as 1 over 20 j omega, which will be magnitude in decibels will be 20 log of omega minus 20 log of 20, right? So this is for this region. And then finally, when you draw it, I'm just drawing the final body plot. So this is magnitude in decibels. This is magnitude in decibels, and this is omega, but this is log of omega here. Right, so I had corner frequencies at 10, 20, 50, 100, right? And when my omega was between 0 and 10, I had a constant slope of 20 log 5, probably. I had a constant slope of 20 log 5. So I'll start from here. I'll start, let's assume this is my 20 log 5. So I'll start from here until my 10 frequency is reached. I'll go like this, constant slope of 20 log 5. So it will be 20 log 5. Then I know when I reach 10, at 10 I have a pole. I know my one pole gives a contribution of minus 20 dB per decade, right? So I will go like this, and it will go till my magnitude is reached. My magnitude is 20 log 5. So my magnitude is this 20 log 50 minus 20 log omega. So at omega equal to 10, it will be 20 and cancel. It will be probably 20 log 2.5. So if you put it, it will be, yeah, something like this.
Sarji,
Uh-huh.
sir, I may leave the meeting now.
Yeah, sure. You can leave. I'm just completing it. So because you had a pole at uh, 10, so you got a contribution of minus 20 dB per decade till this point. So even if you have to point, what is the value of this point? What is the value of this point? You can easily find it from mathematics. Why? Because if you have to find the x, you know this, yeah, let me take it as y1, and you know the value at this y2, you know the value of x. It will be something like this. For example, y1 minus 20 log 5, which is y2 divided by log of 20 minus log of 10, right? So you can easily find the value of y1 from here, which I told you is minus 20 minus 2.5. It is actually, it is 20 log 2.5. You can easily calculate it from this mathematics like slope. Then when you reach here, you have at 20, you have a pole. So at 20, you have a pole. So your slope will be plus 20 dB per decade, but you're already coming with minus 20 dB per decade. So minus 20 plus 20, it will be 0. So it will be 0 till here, 50. So it will be here. Then at 50, you have a pole. So it will be something like this. Then at 100, you have a, at 100, you have, sorry, at 50, you had, yeah, you had a 0. At 50, you had a 0. So it will be 20 dB per decade. And at 100, you have a pole, will be then minus this. So your Bode plot will be something like this. You practice similar questions. It's not difficult, but I'll just summarize it for you. So whenever you're asked to draw a Bode plot and you are given a open loop transfer function, what you will do, you'll first write that in time constant form so that you directly get the corner frequencies. Then you'll mark corner frequencies in the plot, right? And you'll write them in increasing order. So then you will find the value of your magnitude plot using those corner frequencies from the transfer function. And you should know whenever you are putting in the values, for example, here, when I'm putting the value of 10 and before 10, when this omega is less than 10, you need to ignore all j omega terms and only consider this one terms. But whenever you are putting in, for example, you are putting in 20, so you will consider all those j omega terms which are less or equal to 20. So j omega terms including 10 and 20 that can be included, and every other term that will be ignored, j omega term, and only one will be considered. Right. So then you move step by step, find magnitude, find phase, and then you can easily draw it. So there is one type of question which is frequently asked in exams, in competitive exams, where you are given a transfer function and you have to find where you are given a Bode plot and you have to find a transfer function. So you can easily see. So if you are given this Bode plot, you know there is a constant slope from the beginning. It means there is no pole at origin. So if you had slope something like this, minus 20 dB per decade, it means there is a pole at origin. If you had a slope something like this at the origin, it means there is a zero at origin, which gives a contribution of plus 20 dB per decade. So whenever you are given a Bode plot, you should be able to recollect the transfer function by looking at the Bode plot, because you identify that if there is a pole, the slope will be minus 20 dB per decade. If there is a zero, the slope will be plus 20 dB per decade. Then you can easily write that in the standard time constant form, and then you will be able to find the transfer function. Right. So, but the challenge is how to find the value of gain k. So there are different techniques that you like apply then, because it depends on the question. What are the things given? For example, in this question, if you have to find the gain k, you know that when omega is 0.1, this value, you have gain of this 20 log 5. So you'll put omega equal to this value in the transfer function, and then uh, you may find the value of k. Right. So I think now we are running out of time. So you can try your questions, assignment questions. I think you should be able to solve some of them at least. And if you have any doubts, you can reach out. And I'm just stopping this meeting now. Thank you very much for attending.
Thank you, sir. Thank you very much.
Thank you.